Welcome to solverfy.
For A, the problem is use your calculator or computer to make a table of approximate values of the integral from 1 to t g of x dx for t is equal to 2, 5, 10, 100, 1,000, and 10,000. Thus, it appears that the integral of from 1 to infinity g of x is convergent. By computation, when t is equal to 2, 5, 10, 100, 1,000, and 10,000, the integral of g of x from 1 to t is equal to 0.4475, 0.5771, 0.6213, 0.6683, 0.6730, and 0.6734. It appears that the integral of g of x from 1 to infinity dx is convergent, since we can see the value is very, very small. It's always smaller than 1. For B, use the comparison theorem with fx equal to 1 over x squared to show that this improper integral is convergent. For part B, we know integral of g of x from 1 to infinity d of x is equal to the integral from 1 to infinity sine x squared over x squared dx. But we know sine x squared is always smaller than 1, so this is smaller than integral from 1 to infinity 1 over x squared dx. But we know this improper integral is convergent. So by comparison theorem, the improper integral of g of x from 1 to infinity is convergent. For part C, look at the graph here. The red curve is the curve of 1 over x squared, and the blue curve is g of x. We can see the blue curve is always under the red one. And we know the integral from 1 to infinity is just the area and the curve and x-axis. So the integral of g of x is smaller than the integral of f of x. And use your graph to explain intuitively why the improper integral of g of x is convergent. Since we know the integral of g of x from 1 to infinity is the area under the curve, the blue one, and x-axis, we can see when x is greater than 6, g of x is almost 0. So we can guess the area is finite, it's not infinite.